Živijo, Rok, se slišava?
Živijo, ja, vse super.
Super.
Ok, počakamo pa. Tako kot pri vseh prezentacijah, jaz najprej te malo predstavim, pol pa začneš.
Torej vidi se tale screen.
Ja, PLC Programming for Automation prezentacijo vidim. Ok.
Rok. Hello, everybody.
Hello. Yeah, it's time to start the second session of the day. And in our first session with Professor Bachun, we've looked at the sensing part of things, so imaging systems. And now Luca Selak, a PhD, will present the actuation part, which is in industrial applications, mostly related to PLC programming. So Luca is a researcher at the Faculty of Mechanical Engineering here, and his expertise is actually very much related to the programming and automation aspects of manufacturing systems, as well as hydropower plants, which is one of, let's say, his pet peeves in terms of research and applications. So, Luca, the floor is yours.
Thank you. So as Rok mentioned, I'm also teaching assistant for courses from the automation, industrial automation, manufacturing automation. So today I will present you some of the topics I worked on in the past in the field of hydropower plants. Then I will present you the courses in the field of automation. And then I have prepared some short demonstrations of two PLC-based layouts. And finally, I will show you how we use the knowledge for the integration of robots, CNC machines with the PLC. So I will start my presentation with the industrial product service system concept. So this concept was also my basic concept during my research and my PhD. So the main question is it possible to transform the existing relationship between buy-sell relationship between customer and supplier with new business models? So traditionally, the customer is responsible for operation, maintenance of the industrial system, and this relationship normally stops with the supplier of the equipment after the warranty period. And so my PhD was about how to extend this relationship with new business models. So I worked tightly with a company which produces equipment for hydropower plants, actually hydropower turbines, water turbines, and the whole systems for hydropower plants. And at the beginning, the supplier didn't have all the necessary maintenance personnel, maintenance knowledge. And the idea was to support the customer with maintenance from the suppliers. So this company and the hydropower plant is located in Slovenia. Of course, we realized in the very early in the beginning of the project that condition-based maintenance and based on monitoring is the essential part of delivering new business models. And the second, after, if you want to establish monitoring and maintenance afterwards, then you have to gather data from the control system. And of course, the control system is composed of PLC controllers, which will be the topic of the today's talk. To check how does it look, the system control system on a typical hydropower plant. So it consists of a basic control system. So each of the turbine, the generator is controlled with its own PLC. Normally it's a Siemens PLC controller, and the unit controller could control the whole hydropower plant. So the SCADA controls, the SCADA is used to control the systems and subsystems, and normally the hydropower plants and its operating power is controlled from the dispatch center. So our main idea was to firstly to get the data from the control system, and so the concept proposes an additional controller which communicates with the control system, because in the typical hydropower plant you have to assure the security. So you are not allowed to get into the system from outside. Additionally, we identified that the typical control system does not allow monitoring of high frequency phenomena like vibrations, pressures, runouts, and we proposed additional data acquisition system. So all the data are then moved to the OPC, to the data server, which is then connected over the internet to the virtual diagnostic center. So the virtual diagnostic center is a main meeting point for the maintenance personnel, for the experts from different fields of specifics of each system. The virtual diagnostic center is actually a web platform with integrated diagnostics tools. Here you can see the sensors which are typically installed in and connected with the control system. And on the right, you can see the additional sensors used for monitoring of high frequency phenomena. As I said before, in order to acquire data from the control system, there is an interface PLC controller, which is the interface to the main control system, and actually just translates and reads the tags from the control system and makes it available to the outside to read it from the outside system. I think the refresh rate was programmed to for a frequency of 5 Hertz. So you can read it 5 times per second, which is sufficient for the purpose of gathering data from the basic control systems. Typically, these phenomena are slow. For example, temperature changes slowly. OPC server for the company Matricon, which is one of the best servers to integrate it with Siemens PLCs, is used to read the text from the PLC, and dedicated application was developed to store data to the SQL database, and the algorithms which store the data periodically and based on the value change. So if the temperature changes, for example, for 1 degree, then it automatically stores the temperature. This way, we optimized the database size. The high frequency phenomena are monitored with equipment from National Instruments, and a LabVIEW application was developed to monitor the high frequency phenomena. The concept of time horizon was implemented, so you monitor the process before the event and several seconds after events. So what are the events? Events are sudden stop, change of the operating power, start, and similar events, which are interesting for to determine the system condition and state. As explained before, all these data are available to the expert from the diagnostic, from the web portal through different diagnostic modules. So here I can see maybe also the involvement of your country, especially in the field of the diagnostics of different condition state of the systems. Okay, here is one of the examples how we use the system. Here you can see the guide vanes of a water turbine, and you can see that this guide vane is quite large, and it happened that the guide vane didn't follow the reference value, as you can see here. So the green line shows the reference position. As you can see, the reference position changed, and the pressure on the outside side of the cylinder was maximum, and the reference value was not achieved, and this was the trigger for sudden stop of turbine. So this is really a huge problem, and since it was still in the warranty period, the supplier was obliged to solve the problem. And maybe you can give me some advice, or you can think what to do if the guide vane doesn't follow the reference value. Yeah, so the expert gave a proposal to lubricate the mechanism and check if that would help to solve the problem. So somehow the experts used this platform to solve this solution, and the solution, so the guide vane was lubricated, and as you can see, the red, which is the pressure on the outside part of this valve, drastically decreased to the nominal and to the normal operating levels. So this was one example, and so one of the examples how to use the virtual diagnostic system for equipment diagnostics. I will now follow to the topics that I also work with students on small hydropower plants. The hydropower plants, I have access to 2 small hydropower plants, which their size is about 70 kilowatts. They produce about electricity for about 200 households each. And actually the hydropower plants are quite small, and these are the test beds for seminar works for the students that I work with. As you can see, the hydropower plants are in the same river stream. So there's many challenges and many seminars that are already executed in the past in these 2 hydropower plants. I will just show you some of the examples, what we already did, and what are our tools based on which we develop the different kind of systems, but always in order to support the operation and maintenance of the hydropower plants. Here we developed mobile communication infrastructure to enable communication with remote hydropower plants. We used the so-called radius server, which allows bidirectional communication with remote devices, and the system is based on the mobile communication network. We also developed SCADA systems to monitor and control we use LabVIEW for now. A very good alternative is, of course, Python-based, web-based interfaces. In this case, the LabVIEW communicates with a PLC directly via Modbus or OPC data server, and this SCADA interface enables control of the guide vane and therefore the water flow rate through the turbine. We realized that the remote operation and control enables higher availability of hydropower plants, and comparing to the operator, for example, which is located near the hydropower plant, this system allows at least 5% higher availability, and also production output of typically this small hydropower plant. With the students, we also develop mechatronic devices. For example, with the students, we developed linear positioning systems to control the position of the guide vane and therefore output power of a hydropower plant. So our students, these are more or less seminars for the students in the final years or for the thesis, different type of thesis, or as a seminar work in final years in different courses. For example, in the left, they developed a PLC-based application to control the position of the linear table, of this table, using the absolute reference sensor. And the step motor is used to control the position of the table. Based on this system, last year, we developed a more advanced product, actually, which is based on the nanotech drivers, which enables also so as you can see on the step motor, the encoder is installed, which enables monitoring of the torque on the motor. Since the torque is important because it may happen in a turbine that it gets clogged with leaves or similar debris. So it's important to monitor the torque when you move the linear table. The students, more or less, they don't work on the machines. We have technicians which make parts, but they do program the functionality, which is specified normally by teachers. Here I would like to show you the project, which I'm quite proud of. Maybe it's nothing special, but here you can see the device to monitor the water flow rate in hydropower plants. Just to give you a reference, there's about 400 hydropower plants in Slovenia, and most of them, or a few years ago, they were not obliged to monitor how much water they took from the river. And of course, it happened that the operators took more water from the river than it is allowed. And we developed a system and we demonstrated that this system can successfully and in a cheaply way monitor the water flow rate of hydropower plants. And we achieved that now when the government is granting the concessions for the water withdrawal, they require that each withdrawal location, water withdrawal location, needs to be monitored, and the data needs to be available on the web page. So we developed a low-cost system. It's about the electronics. It's about 50 euros, and I always say that monitoring is cheap. The highest cost is so the electronics is cheap, but the housing is normally more expensive than the electronics. Maybe it's interesting that we have to develop a water level measurement system to measure in a range of less than 1 millimeter. So with the water level changes for less than 1 millimeter, that's the resolution of the sensor. And we achieved it with accelerometer, because the conditions are, in industrial, are quite harsh. One student also developed a weather monitoring system to predict the water flow. And last year, one student also developed a smart control system. So as you can probably understand that, so we have 2 hydropower plants, one after another. And if the first hydropower plant makes a disruption, if it stops suddenly, then the water affects directly the second hydropower plant. Maybe this situation is controllable, but for example, in Austria, there are 40 hydropower plants, small hydropower plants on one river. So they do affect to each other, and they have to communicate with each other. The student, for example, measured the transfer functions, and he demonstrated that the transfer functions can be used to control, for example, the second hydropower plant based on the data it gets from the first hydropower plant. So that is the first part of my presentation. Now I will go to the courses. So I'm involved in the manufacturing automation courses in the first level and also in the second level. In the second level, I'm involved in the flexible manufacturing system. But as you probably heard, the courses are changing in our faculty. But I think the knowledge will be more or less similar, but just organizational changes will happen or are already happening. Anyway, the manufacturing automation course is divided to 4 topics, and all the topics are oriented, practically oriented. So firstly, with the students, we develop a control device for 100% quality control, and within that main topic, there are 4 tutorials practically oriented, so that students have to program, have to wire the system, and actually everything has to work. The second part is CNC technology. In CNC technology, the students learn the elements of CNC machines and how to wire it, how to use it. Actually, it's the CNC technology is a basic building block of typical mechatronic system, and that's why we work on CNC technology. But we are not limited only on CNC. So technologies can be used on different types of positioning systems. Within CNC technology, the students learn how to use PLC, how to use CNC controller, and how to, briefly, we learn the students how to use the G-code and how to integrate CNC with laser scanner. The industrial robotics will be presented tomorrow. And in the final part, the students integrate the CNC and robots with the PLC controller. Okay, I will go now through these tutorials. As I said before, the students that I teach are in the level 1 and the level 2. So in the level 1, the students come from technically oriented high schools. And I have sometimes problems that some of the students do hear some of these topics already in the high schools. Now, for example, CNC technology, I would say one-fifth of students have quite a deep knowledge on CNC technology, some on industrial robotics, and even some on PLC controllers. But some of the students, they don't nothing. So it's always quite problematic to, sometimes at least one tutorial within each of the topic is oriented to bring the students to the same level. In the level 1, especially students which come from the high schools, technically oriented high schools, sometimes they have problems with writing, but they're already in the 3rd year, and after the 3rd year they have to make a thesis. So we do require to make a report from the development of a control device. This way they practice writing, grammatics, how to to use the proper form, the same way as they use it when they are writing the thesis. But so, as I said, this is only for the students from the level 1. If the students in level 2, they don't have these problems. So in the first part, the tutorials are oriented about device for 100 quality control. Here you can see the device. So this is the part put into the fixture, and the device needs to, the dimensions of this part, which is, by the way, it's apart from this car seat. And this is an example part which we work on, and we have to make a system for 100% quality control of each part, especially to measure the dimension, the position of the dimension between two rods. And so the tutorials are organized in the following way. So firstly, we learn the students how to use LabVIEW. We are using LabVIEW as in the tutorials. to program the control device. LabVIEW is mainly, and the equipment from the company National Instruments is mainly used to program control for signal analysis, then data acquisition. So the students learn basic programming concepts. And from my experience, they do learn quite fast. So the while loop, the feedback node, the for loop, case structure, local variable, they don't have some big problems and issues. Maybe about LabVIEW. The LabVIEW is a license program. We have academic license here in the faculty. I think around half of the laboratories do use LabVIEW for research work. And I think for each lab, the license is around 200 euros per year. So this is academic license, which is all the models are available. There's also academic edition. There's also a community edition of LabVIEW and student edition. So the community edition is, as you can see, it's free, but to use it for personal projects. The students also have a student edition, which is free for 6 months. I think they realized that that Python, for example, it's a real alternative software environment, and so looks like they go to the direction that LabVIEW is going to be free in the future. About certifications, so their National Instruments LabVIEW do offer some certifications. I know that Slovenian representatives in the past, they organized the certification programs. I never attended the certification programs, but I would say the level 1 is, I would make this moment the level 1, but maybe for the level 2, I would have to learn a bit. So the LabVIEW is used by Slovenian companies, especially those that work in the automotive industry, especially to develop control devices. So it's a software that it is used in our industry. Okay, so the students in the level 1, we are using the inductive sensors. The students have to measure the transfer function of the inductive sensors. Then the transfer function is implemented in LabVIEW. So they wire the system. We have, I think, 5 data acquisition data devices. It's a entry-level data acquisition device. And since I have only one, this type of system, the signals are then transferred to all the devices. So the students share the signals. And then the students have access to, each of the students has access to its own laptop, and they program individually, or they also have an opportunity to remotely connect to the laptops. Some of the students, they don't have laptops, they don't have a LabVIEW installed on their laptops, and therefore they have remote access to the LabVIEW. So it's not necessary for them to install the LabVIEW on their laptops. So the students have to develop a user interface for 100% quality control of these parts. In the level 2, I extend the the task by using open source Arduino or similar platform for data acquisition. And also in this case, they use Levio as a user interface, as a data acquisition device, and they individually develop the same system, but this time based on Arduino. For example, they develop for 2 sensors, but the concept is the same. Even they could use it for many more sensors. The network shared variable is used to further extend the functionality of developed system. For example, many times in the industrial environment, there are more devices, and one operator has to develop, has to monitor the whole production environment. And with the students, they learn what are the elements of the local area network, how to establish a local network, and then they add the functionality of remote monitoring of the production system, again based on this control device. And finally, they learn also how the network for data storage is composed, what are the elements, but they more or less only use this pre-prepared environment. We are using MySQL database management system, and the student learn some basic instructions how to store and how to retrieve data from the database. And since the Excel is normally present in the production environment, we use Excel for data presentation, the retrieval, and plotting. So this was the first part. The second part is about CNC technology. Again, CNC technology is based on a desktop CNC machine, which was developed in our lab a few years. Well, I think it's already 10 years ago. We have 2 desktop setups, desktop CNC machines, so the students can work on these 2 machines. So the purpose of these tutorials is firstly to get familiar with the CNC technology, from the step motor to the controller and G-code and CNC programming. So in the beginning, the students get familiar with step motors, what the characteristic curve of the step motors. They have to know how to select and wire the step motor. They need to be able to calculate the resolution of a position movement of a machine table, then the maximum speed, and of course, according to the transmissions used in a specific CNC machine. The students need to wire all the elements, and we are using the Gecko drives. They wire the step motors with a Gecko drive, and then with power supply, and they wire the end switches, the limit switches, and then they set up the CNC controller. In the past, we used Linux EMC CNC controller. Actually, we still use it, but last year I changed the CNC controller to to open CNC controller, which is based on the firmware GRBL HAL with a TNC microcontroller-based platform. And the students also need to understand step and direction control signals for the step motors. We are using the step motors from the Nanotech company. There are also nice simulation tools on their web page. In some of the subjects, the students also need to know how to program the movement of step motor by individually controlling the coils of a step motor. And yeah, this simulation is quite nice starting point. And this CNC controller, the student needs to understand the elements of a CNC controller. Actually, this CNC controller is quite interesting because it supports 5-axis and 5-axis based CNC devices. And it also supports quite fast step generation signals. As you probably know that, so to have machines very accurate and very fast, you need to be able to produce really high step rates of step signals. In this case, I think 150, it's a maximum step rate, which transforms to speed rates of several decimeters per second. So the controller is, I think, is the future of at least some segment of CNC systems. Also, the price is quite competitive. I think you can get this CNC controller for around 60 euros, but it's true, you still need a laptop, more or less, as a user interface, and to have a keyboard as a jog system. So the students learn some basic G codes, but I have to. So the focus of these G codes are more on control of a CNC, but not, for example, from the CAM perspective. We don't learn, at least not in deep, how to program machining operations. Additionally, this firmware is very interesting because it enables development of custom programs to control the CNC machine and the positioning systems. So we are using EO G-code sender. It's of course, all the sender is open, and the students get familiar with how to control and use the CNC machine, and also how to set up one axis of a CNC machine. So they go through all the necessary, they go through all the parameters how to set up one axis of a CNC machine. Here I give you some interesting links of these systems if someone will need additional information. Through years, I came to the conclusion that it's important for the students to also know how to use a CNC machine for machining some prototype parts. And as a homework, they also make some simple G-code, and our technician then machines the parts for them. And we are using Kanban software and web-based tools to simulate and write the G codes. The CAM-BAM, I think it's a little bit more, the license is around $100, and it's not limited to the number of computers. The laser scanners are very important in industrial environment, and we don't teach the students of reverse engineering, but how to integrate the laser scanner with the CNC machines. There are numerous applications, and so this is the laser scanner which Drago developed a few years ago, and we use it in the tutorials. I give the students some building blocks, and then especially for the students in the second cycle, they are already able to work with these tools individually and to make some seminars using the laser scanner and the Gurabala CNC controller. So here you can see the image acquired from LabVIEW of a laser line. The image is transferred to a line, and this is the starting point for the students to make their own seminars. So the students get this part of the code. So to integrate it with a CNC machine, typically the coordinate systems need to be transformed. So the laser line needs to be transformed, rescaled, rotated, and from this line, then we generated the G code, and the G code was then transferred into the LabVIEW program, which was custom developed to simply control the CNC machine positions. And finally, we integrated both systems. For example, to write with a pencil and go to this freeform shape, this random shape. Later, I gave the students some of the seminars. For example, here is the seminar when we put the workpiece on the machine table, and then the software needs automatically to find the workpiece and to transform the G code and write it on the randomly positioned part. For example, sorry. Okay, I have few movies. I'm not sure if it's going to work, but yeah. So that was one example. The second example was to follow the surface of the workpiece, with a pre-specified offset. So it's not, so the students had to use the Clipper library to offset the profile. Then, so as I showed before, so this example was again the example of automatically finding the object and then writing the code on the randomly positioned object. So the students, before they scan, for example, they scanned the whole machine table, and then it took them, let's say, 1 minute to process all the images. And for example, these students here, they developed the concept in a way that they firstly find the object and then try to find the edge of the object. And in this case, the processing took only, I would say, less than a second, but the positioning and scanning took maybe 10 seconds. Okay, this example shows the sim tracking. So here is a sim, and in the first example, the students firstly scanned the sim, and then the machine was moved in the middle of the sim. So these were the seminars instead of the second colloquium for the subject, for the course flexible manufacturing systems. So I will skip the robotics. The robotics will be explained tomorrow. And now I will go to the PLC automation. For the students in level 1, we have a dedicated course just oriented toward PLCs. So these are the students, technically oriented students. Other students in the first level, they get familiar with the PLCs in the basics of mechatronic systems. But it still may happen that some of the students don't hear, even in five year, if they don't choose, for example, the basics of mechatronics, they don't hear the course or at least basics of PLC automation in the 5th year. So in the tutorials, it's sometimes necessary to explain them at least basics, even in 5th year. But from my point of perspective, which is the integration of PLC, CNC with PLC, robot CNC with PLC, I try to learn the sequential function chart, and which we realize it in function block diagram. Since not all the PLCs do not support all the programming languages, but the professors do learn sequential function chart and the realization of it in function block diagram. So function block diagram and sequential function chart are systematically, we teach them systematically, but of course in some specific projects, the students get familiar also with ladder diagram. And I think also the structure text, but not with me. We have a nice layout to learn students the sequential programming. So here is a conveyor belt. It has 2 photo transistors, one on the left side, one on the right side. We have a start button, a DC motor which controls the movement of a workpiece on the conveyor belt. And typically the functionality, the required functionality is given in a descriptive language. So the belt is stopped until the workpiece is put in front of the left phototransistor. Then it starts movement on the right side. And when it gets to the right side, it stops for a few seconds and then moves back to the initial position to the left phototransistor. And then the operator needs to remove the part, and to repeat the cycle, it has to put it back, and then the operator again clicks start and so on. the cycle is repeated. This is the layout that students work with. I think it's important for the students to have some kind of layout, because you cannot directly go to the serious systems like real robot. So we learn the students the SFC, the realization of SFC in function block diagram. Okay, I won't go into details. And the students use the logo software environment and the logo PLC. So the logo is a main PLC controller. Well, we still have to understand that the students are mechanical engineers. We are not faculty so it's another faculty to learn different types of PLCs. The controller has 4 relay outputs and 8 inputs, but it can be extended. Logosoft is used for programming and simulation, and then the programs are transferred to the logo. So the students go step by step. So we give them a SFC, and they realize the SFC in FBD. Then we give them some more advanced examples. So in this case, the output 1 is active in 2 steps. So the transition 2 resets the output 1 and output 2. We give them then different more advanced tasks, which are not related directly with the specific problems, but they do need to understand how to realize FBD from SFC. Here is the example from the exam. So we give them this example, and then they need to realize this example in FBD. Okay, I have to admit, this is more for the students in the second cycle, or it's a more advanced example, more advanced task. But if you need, here are 2 examples. And this is the parallel configuration example. So after they know how to use the SFC and how to program PLC, then they realize the conveyor belt system. So they study the electrical drawing. They try to understand how to wire and of course they do wire the system with the PLC. So during the Corona times, the PLC, the wiring was pre-prepared and just programmed and remotely operated the system. They go step by step. So firstly, they test the hub bridge, which is used to control the direction of the DC motor. Then try to understand how the photon transistor works. And then they specify the SFC, and then they realize it in FBD. And finally, they test its operation until it works according to operating requirements. Normally, it takes almost 2 hours to finish this task. So after this, I will skip these details. So this was the way how the students worked remotely. So the camera from the laptop was pointed directly to the setup, to the layout, but otherwise they programmed in Logo on the laptop, of course, remotely. It was also required to have to install Logosoft and to use Logosoft during the exam. And after they finished the task, they uploaded the code, the image of the Logo program. This is the solution for the conveyor belt system. Yeah, there are some details which are important to be really precise. Otherwise, the program doesn't work. For example, here is the negation. They need to be really careful not to forget it, because maybe simulation looks like it works, but in reality, it's not necessary that it works. Okay, so just as a short demonstration, I prepared the demonstration of this system. So here I have two demo systems. So the left demo, which will be presented a little bit later, and the right demo. Actually, we already know how it works. So we use the batteries for power supply, 12-volt batteries. So the PLC controller automatically starts the preloaded program. And as we said before, so the part needs to be positioned on the conveyor belt. Then the operator clicks the start button. The workpiece goes to the second side, to the second transistor. It then stops. But of course, whatever I click in the meantime, nothing happens. So this is the purpose of sequential programming. And even now, if I click stop, nothing happens. So because the workpiece needs to be removed. And even now, if I click the start, when the workpiece is not present, the conveyor belt doesn't start. When I put the workpiece back, so it starts the sequence. So this is the tool that students use during tutorials. And it works quite well. Maybe sometimes they have problems with hub reach wiring, because if they wire it wrongly, then they can make a short circuit. But hopefully, thankfully, nothing explodes if they don't wire it right. Okay, that's the right example with industrial PLC controller, but for the purpose of this presentation, I also developed or tested the same system, but in this case by using the Raspberry Pi and Open PLC software environment. Maybe before I go to this example, I can show you the simulation in Logosoft. So the simulation, for example, enables really nice simulation of the button. If it's different types of button operation, normally closed, normally open. And for the students, it's really easy to use this software. But so in this second example, I tested the software Open PLC. The software is open and can be installed in as editor in Windows-based operating system or on the Raspberry Pi. The software enables programming in SFC or FBD. In this case, I prepared the FBD, but there's also an option to use the SFC, and also the simulation can be made, but I think it's a little bit not so user friendly. So if we go here, you have manually click. For example, now we are in step 2, I think. So I have to manually click on the input and then click toggle value. And then I have to manually click, for example, again, toggle value to disable input. And so now I have to go back to input 1. So you have to understand a little bit more what is happening with inputs and outputs. But otherwise, you can also use the OpenPLC software, which I find it quite interesting. So now we are in the first step. I think we have to make it back. Okay, so when you program the software, you can transfer it to the web interface. So there's a web interface which is used to upload the program on the Raspberry Pi. So now we are connected via web interface with the Raspberry Pi. And Raspberry Pi, I uploaded before the program, so conveyor belt. So I did it today in the morning to check if everything works. And the program is now in the running state. In here, in the monitoring tab, we can check the inputs and outputs. So now so let's go back to the camera. Now the battery is disconnected. I will reconnect the battery. So I hope now the Murphy won't be involved, because typically in real systems, you never know. So as you can see, when I plugged on the power supply, the outputs changed its state because the phototransistor work in normally open. Yeah, I think so. So if I manually click, put the part in front of the phototransistor, then the output automatically online changes. And again, I uploaded this example to the Raspberry. As we said, we have to put the part in front of the first transistor, and then we click start, and then it moved to the second. Looks like we have a Murphy. Move to the second phototransistor, and when it comes back, it should work. But looks like it doesn't work because I have to admit I have some wiring problems, and because in the morning it works. So this is one of the disadvantages of this type of systems. because you can have one wire and yeah, the system doesn't work. So maybe till tomorrow I will try to find the error, but the error is in the wiring. Maybe a bad contact and nothing works anymore. The Raspberry Pi is a 3.3 volt system, so you need to use the voltage divider to divide the input voltage from 12 volt to 3.3, and the relay output board is used to convert 3.3 volts to relay output. So this is all what needs to be additionally implemented comparing to the logo PLC. But of course, you don't need the PLC. The Raspberry Pi based PLC is of course cheaper than Siemens based PLC. So when the students know how to program in SFC, then they do learn how to program robots. And here is the example from last month. The students had to develop an application to pick up the workpiece with the yellow robot, put it on a CNC machine. CNC machine makes some drawing, machining operation, and the green robot picks the finished part. Again, the students developed a SFC. Then they developed a G-code program to handle the input and output of a CNC controller. This is how it looks, our work in the lab. So one group of the students worked with the yellow robot, one with green, and one group with the CNC controller, with CNC machine, and one with PLC. So this was a kind of seminar which took about 2.5 hours. And finally, so the first robot. Maybe this is not the perfect example, but it's always, we never film enough and make enough pictures. So the first robot picked with the camera the workpiece, then it put it on a CNC machine. The CNC machine makes some simple G-code. We use vacuum table, and the last robot picks the finished part. And so the green robot is a collaborative robot, so it doesn't need the fence around, but it's a little bit slower comparing to the yellow one. So the robot, the cell finished its work. The robot finished its work, and I finished my presentation. Thank you very much for your attention. Thank you.
Thank you very much, Luca, for the presentation. I think it's very interesting to show that a lot of these things can be taught even remotely, as we had to do during the COVID pandemic, as well as using very low-cost equipment to teach these industrially relevant concepts. So please, if you have any questions from the public, just go ahead.
Hello?
Yes.
Can you hear me?
Yes.
Yes.
First of all, thank you for your interesting presentation. This is Dr. Moayed Al-Mubayed. Well, actually, I have just two questions. The first one related to the software used in the automation. Most of your experiment related to LabVIEW. Did you use MATLAB in your experiment with students?
For these courses, we don't use MATLAB, or maybe for some seminar works, the students use MATLAB, but they don't learn it within these courses, not MATLAB. The first question was which tools? So as I said, LabVIEW, Logosoft, CamBam, yeah. And yeah, different open tool softwares for CNC technology.
Another question, Luca, you mentioned about some project related to the real-time experiments. Well, actually, most of them are very interesting. However, I need to ask, do you use a GPRS module with PLC, for example, to communicate between these controllers, like for the water level, or what is the communication used?
Well, if I go back to the hydropower plants, so actually we have in a hydropower plant, we have, for example,
this one.
Yeah, this one here is it's a computer located in a hydropower plant, actually next to the turbine. But we use, because the dam, the water withdrawal location, it's 500 meters away. So we use the mobile technology, mobile transfer.
I see.
To transfer it, actually, like this, to transfer it to the faculty. And then from the faculty, we transfer it back to the powerhouse. It takes about, I think it's the late time, it's because of the edge technology, it's about 3 seconds. It takes the data from the dam or faculty back to the powerhouse.
And for the Raspberry Pi, you use Raspberry Pi 4 or 3?
It's free, still free. But the editor also works in this Raspberry Pi. We checked it.
When you use the Raspberry Pi, you download, for example, another version for LabVIEW in order to work with Raspberry Pi. Is okay?
I didn't use it yet. So I didn't use Raspberry with LabVIEW yet. But
It's available in general, I mean.
Yeah, in general, I think it is, yeah. But I didn't use it yet. So I used OpenPLC for that project.
Yeah, I write it. Thank you. Maybe last question for the brushless DC motor you used. You know, there is kind of Hall effect sensor brushless DC motor. Did you use this version or without sensor? Because I mean the controller will be different.
You mean for the CNC machine? For the CNC machine, we use step motors, not DC, brushless DC.
You mentioned one of the experimental brushless DC motor. I think it's a separate one.
Maybe you mean this one for the linear table.
I think when you talk about the drivers and sensors, I don't know.
Yeah, maybe here, for example, this driver here, it enables connection of the brushless DC or a step motor with encoder. But typically, no, we don't use some other drivers with CNC.
So for example, when you're teaching your student about the brushless DC motor, did you talk about the torque and the modeling of this, or just like the controlling of this kind of motor?
Maybe I didn't told right, but I didn't tell right, but we learn only step motors, the student, yeah, not the brushless DC.
Thank you very much for your presentation.
Thank you.
Thank you. Yeah, just to comment on that, we have various courses in the scope of mechatronics. So What Luca is talking about is the part which deals with industrial automation. But then we do have other types of motors that we go over during the lectures and do have some demonstrations during the tutorials. But it's again, other courses, separate courses. We have one called the Basics of Mechatronics, where we do a review of different types of electromotors and the way they're used in mechatronic systems. Okay, thank you. Are there any more questions? Any additional questions? Okay, if not, thank you all again for attending the session, and a special thanks to Luca for a very practical, very hands-on demonstration. Yeah, so that was really great, I think. So thank you, Luca.
Thank you.
Thank you.
Okay, and see you in about an hour and a half for the third session of the day, dealing with IoT and blockchain and very modern technologies and things that we use in the faculty. Thank you all. See you later.
Thank
Thank
you.
you.
Bye-bye.